All right, it's 3:30, so we'll go ahead and get started. Good afternoon, everyone, and welcome to today's EOL seminar. I am Sarah Woods, and on behalf of EOL, I'm pleased to introduce Dr. Sebastian Hoch. Dr. Hoch is a research associate professor in atmospheric sciences at the University of Utah with over 20 years of experience studying atmospheric processes, with a focus on observations in the atmospheric boundary layer. He received a doctorate in natural sciences at the Swiss Federal Institute of Technology in Zurich, Switzerland, before continuing his career at the University of Utah. He specializes in complex terrain and boundary layer meteorology, meteorological field studies, and meteorological instrumentation. Applications of his work have related to air quality, fire weather, and fog formation. Dr. Hoch has experience with a wide variety of atmospheric sensing devices, including a scanner, Doppler wind LiDAR, a SODAR, ceilometers, radiometers, and surface energy balance measurement equipment, and has taken part in over 25 national and international field experiments, 4 of which were supported by EOL. He has just recently returned from Zermatt, Switzerland, where he conducted LiDAR observations of banner cloud formation in the lee of the Matterhorn. Despite being career-line faculty, Dr. Hoch has been regularly teaching a course on mountain weather and climate and has taught UCAR Comet training lectures for forecasters of upcoming Winter Olympics. He has advised PhD and master's students and has co-authored over 55 publications. Please join me in welcoming Dr. Hoch for his seminar titled Observations of Radiative Heating and Cooling in the Atmospheric Boundary Layer Under Clear Sky and Fog Conditions. As a reminder for those of you online, please submit your questions in Slido at the bottom of the screen, and we will read them out at the end of the seminar. Dr. Hoch, welcome.
Thank you very much. Well, thank you very much for welcoming me to the EOL seminar, and thank you everyone who gave me a nice introduction to NK-EOL today and the nice conversations so far. I'm excited to talk about research I've done on radiative heating and cooling in the atmospheric boundary layer. It was a little hard to decide on what presentation to give you. I could have talked about banner cloud formations on the Matterhorn or dust emission on the drying Great Salt Lake bed, but I decided to touch on a topic that I thought is interesting and in the realm of micrometeorology today. So this is actually an EOL picture of an EOL experiment, the CFACT campaign, the campaign recently conducted and supported by EOL. And of course, I would like, before I begin, to acknowledge that this work has been very, very collaborative, that I've not done this work by myself, but it's teamwork with, where mentors and mentees were involved. All right. As an introduction, why studying radiative heating and cooling near the surface? So radiative cooling is one of the terms in the temperature tendency equation, and I'm showing this here. So you have the storage term, and you have the advective terms, molecular diffusion, and then you have the so-called divergence term, where you see the rate of change of shortwave fluxes, longwave fluxes, and then sensible heat flux in the atmosphere that determine the outcome of temperature. And as an example, I'm showing here also a time series from the CFACT campaign taken in Heber Valley, Utah, in February 2022 on an EOL-provided flux tower. And these are temperature fine wire sensors located between 1 centimeter above the surface all the way up to 32 meters above the surface. And you're seeing here, shortly after sunset, a strong drop in temperatures, a cooling, it was a clear sky night, and then a rapid increase in temperatures after sunrise. And this then translates in so-called temperature tendency or observed heating rates that can be expressed in different units. So this is here in, typically I use Kelvin per day. So you have a cooling here of about 150 Kelvin per day, which corresponds to about -6 Kelvin per hour. And then heating and observed heating on the order of 100 Kelvin per day or 4 Kelvin per hour. So these heating rates and the rate of changes of the radiative flux in the layer can, or what also can be abbreviated as RFD, or clear radiative cooling, can expressed in these units either in watt per square meter per meter, or in Kelvin per day, or in Kelvin per hour. So I tend to use Kelvin per day as a unit. So I wanted to make you familiar with that. So when we look at radiative heating and cooling, so why are we really interested in this? And one is kind of this fundamental idea of understanding how the atmosphere works. So what processes shape the thermal structure near the surface? And when we look here actually in detail, in this evolution of the temperature cycle, and we take a reading here. This is an example at 5:20 in the morning. We're actually seeing something that we don't necessarily expect. And this is that the coldest temperature is actually not observed directly adjacent to the surface, but it's somewhat elevated from the surface. So these are kind of fundamental observations that drive to understand the different processes that determine the temperature near the surface. I'm also coming from the mountain meteorology background, and typically temperatures in basins are topographic basins are typically places where record low temperatures are being observed. So one example in Utah is Peter Sinks that holds the cold temperature record of -56 degrees Celsius. And so basins are known to produce very cold temperatures. But on the other hand, in other basins, like in this Kennecott copper mine, which is actually just adjacent to the Salt Lake Valley, we took observations there, and we're actually seeing that the temperatures within the mine basin tend to be much warmer than outside the basin within the wider Salt Lake Valley. So one question is whether it's the counter-radiation from the sidewalls that lead to warmer temperature and doesn't allow a basin of the scale of this mine to cool efficiently or as efficiently as a flat surface or a valley. The third motivation for studying radiation near the ground is its importance in the formation of the life cycle of fog. So here I'm kind of showing the complex interactions that control the fog-water balance, where different processes interact to determine the outcome. So we have the radiative energy change here on one side, but then we have the microphysical processes and then turbulence processes in the other triangle, and these are tightly connected. So when we look at radiative transfer, it's really that when you introduce fog, water, or ice into the radiative transfer near the ground, then the exchange is not in the absorption bands of water and CO2 anymore, but you have water droplets. So the radiative exchange becomes a function of the liquid water content, droplet size distribution, and so on. And these radiative processes are directly coupled with the microphysics and the turbulence to determine this outcome. And when you study marine fog, in a marine fog environment, there's typically strong sensible heating that's compensated by strong advective warming, and it's the tongue on the scale is basically the radiative cooling that can determine the outcome, whether fog is forming or is dissipating. And so there's also a good overview by Varstedt et al. On these connections. So these are kind of three different motivations of why I'm interested, or why radiative heat exchange near the surface is being studied. So a quick historic overview of these observations. So on the modeling side, the first studies of looking at the effect of a temperature gradient on the heating and cooling in the atmosphere was by Flegel in the Journal of Marine Research. And he used Alsacer diagrams to calculate long-wave radiative fluxes. And what you see here is that under stable conditions, it results in a layer of radiative cooling close to the ground, but immediately near the ground surface, there's actually radiative heating that's occurring. The first observations of radiative cooling and heating near the surface were conducted by Funk in 1960, and these observations were allowed because the first instruments were developed that were sensitive enough to measure small fluxes, small differences in the radiative fluxes. And here you can see that during the evening hours, he recorded, in the top here, you see the radiative heating rate, so there's some cooling that is observed away from the surface. Now, in the following years after these studies, there were a series of investigations now that term in the temperature tendency equation was studied, and there was a mixture of observational and modeling studies, and they were sometimes contradictory. So some observed heating under stable conditions, other cooling. Some authors stressed that the radiative flux divergence was quite important for the cooling in the evening, and other results showed the opposite. So there was quite a back and forth in the results. And that actually led to a graph in one of the important books in mountain meteorology and textbooks that are still used nowadays, and probably many of you have that book in your bookshelf, by Stahl, 88, The Introduction to Boundary Layer Meteorology. And typically here under stable conditions, it's shown that there's radiative cooling immediately to the surface. But then there's this small dashed line and saying that some of the results report radiative heating near the ground. And so this led me in my misspent youth during my PhD time to investigate that a little bit further. And I used the back then en vogue radiative transfer called Motron to do some calculations and some idealized calculations of the outcome of different temperature stratifications. And it was during a project when I did also research on the top of the Greenland ice sheet and on a 50-meter flux tower, and where we observed temperature gradients of this magnitude. And so I was trying to both model and measure radiative flux divergence on this tower, and that's why you see this data. So I looked at the temperature profile as a function of a temperature difference between 50 meters and the surface, and then this factor kind of gamma that controls the shape of this temperature profile. And the outcome is here that is this radiative transfer model was delivering results very closely to what Flegel in the 50s had in using Alsacer diagrams. And where you see if you have strong temperature inversions under stable conditions, you see a layer of strong radiative cooling in layers above that surface, but immediately near the surface, you actually see a heating effect. And If it's opposite, if you have unstable conditions, it leads to the cooling above and a small heating contribution near the surface. And so next you can use the value of gamma to kind of compress that temperature gradient and increase that near the surface. And when you do this, you kind of see that you are getting stronger and stronger radiative cooling rates. But nevertheless, near the surface, you still observe radiative heating near the ground. So, and as a next step, of course, what is very nice is your model is spectrally resolved. You can see the spectral distribution of that radiative heating, and that is now shown for one of the stable conditions where I think I had 10 Kelvin difference here in the lowest 50 meters. And you nicely see that the radiative cooling and heating where it is generated, and it's the strong absorption bands of water vapor and CO2. And you see the heating near the ground where you have the black body radiation that's initially emitted near the surface where you have the heating occurring. So these are idealized model calculations, but of course in nature you never have these beautiful temperature structures. So the modeling challenges really are that the model really heavily depends on a very accurate representation of the detailed structure of your temperature and humidity distribution. And so you very quickly get different model results if you only change the shape of your curve, or if you even introduce discontinuities in your temperature profile. So that can lead to strong outcomes. So therefore, it might be also valuable to have measurements to kind of compare these model results with. So next I want to then introduce you to some observational approaches to measure directly resolve radiative cooling in the atmosphere using a tower. And so here I'm just showing the conceptual setup that was came up with to measure this during fog conditions, during the cold fog amongst complex terrain research on the EOL ISFS 32-meter tower that was deployed at the Deer Creek supersite in Heber Valley. And so the idea is to deploy couples of pure geometers measuring long-wave radiation at different heights, both in and outgoing long-wave radiation at 32 meters, at 7 meters, at 2 meters. That was typically on the sawhorse type structure, and then have one sensor coupled very close to the ground at a half a meter. It's basically as close as you can get to the surface. And that will allow you to resolve radiative cooling or heating, or the convergence, which leads to radiative heating. If you have a convergence of the fluxes, if you have a divergence of the fluxes, that will lead to radiative cooling. And that ultimately will affect whether you can have condensation or evaporation of fog water. So, and this was basically how it was realized. And you kind of see the couples of pure geometers here at 32 meters, at 7 meters, here at the Sawhorse, and then at half a meter to realize that at the CFAC Deer Creek supersite. The challenges to do these observations is that we are interested in very small differences in radiative fluxes. And if you look at the manufacturer accuracy of the Kippensonen instrument, it will tell you something in percent. It's probably on the order of 5 to 10 watts per square meter, depending on this. So in order to resolve smaller differences, it's very important to look at to carefully characterize the instrument and to perform a relative calibration of the instruments. The nice thing is we're not really interested in the absolute value of the flux, but in the relative accuracy. So in order to do this, we first deployed this instrument on one of these sawhorses, and you see here this relative calibration setup. You see 4 up facing and 4 down facing pure geometers. And you have the calibration coefficients C, and then you have the Steinert-Hart equations, Steinert-Hart coefficients of your thermistor equation. And you can vary these in its framework of uncertainty, and under the assumption that the sensors are observing the exact same flux, you can determine these coefficients. And when you do this, you're here's for this relative calibration at the Deer Creek supersite, you're seeing this 3rd pure geometers against the reference, which was, here I'm using the reference as the mean of all the 4 instruments. You're seeing that you get a very small standard deviation. Here's one that wasn't performing quite as well, but you're seeing that these differences are well within plus minus 1 watts per square meter. Now, in order to do this, you really need to do the best to get the best possible measurement. So you ventilate the sensor to don't shock it with strong temperature changes. And you're blowing somewhat warmed air over the dome of the instrument that there's no particles forming on it and so on. And one thing that needs to be done and that introduces problems with this approach is that you need to correct for different fields of view of the instruments. So the field of view of your radiometer at the top of the tower is seeing a much larger footprint than your pure geometers that is down facing at 0.5 meter above the surface. So it's a question of representativeness of the emitting surface. So unfortunately, well, the next step then is to start converting these radiative fluxes into heating rates. And of course, that depends on your layer thickness, because you're looking at a change of a flux or a bulk layer. And so if you have a thick bulk layer, your error in your flux uncertainty translates to a smaller error in your radiative heating rate. It's a larger uncertainty if you're uncertain if your layer is very thin. And you're seeing here, this is about 3 Kelvin per day for the entire layer between 0.5 meter and the top of the tower. But if you're looking at the layer between 2 and 0.5 meter, you know, your heating rate uncertainty gets up to 60 Kelvin per day. So that's a very large, if you remember the time series there, that is on the order of the magnitude of the changes during that time. So unfortunately, I wanted to show you some data from the CFAC campaign. There are a few issues still that I haven't ironed out with the data set. I'm seeing that there's slight variations and shifts during times when the tower was lowered, and I haven't really figured out exactly what this is. And many of you might be familiar with these types of observational problems. But I therefore want to show you some results from another project where I took these measurements, and that was the meteor crater experiment in 2006, where I also took some observations in the floor of the Arizona meteor crater. And here you see a picture of this tower, and sensors were mounted at 0.5 meter, 2 meter, 5 meter, and almost 9 meter. I think it was 8.9 meters above the surface. And so what I'm plotting here is now diurnal cycles of both the in and out going and net radiative flux divergence, or converted into heating rate. And what you're seeing here, that is between the layer between 0.5 and 2 meters. What really sticks out is that we get really tremendous radiative heating during the day. That is governed by the convergence of the outgoing flux. and that also during nighttime, when we have stable conditions, we see a net radiative heating near the surface. As we go slightly up into the atmosphere, so between 2 and 5 meters, we're still seeing that daytime, a lot of heating is actually being caused in the atmosphere due to the convergence of the radiative fluxes, while during the night, oops, I knew that mouse would do that. Let's see, I need to try to find this again. So, okay, so here we're still seeing that the divergence of the outgoing flux dominates, or here during the daytime it's a convergent. At the nighttime now we have a radiative cooling at that height. And so as we go up, the daytime radiative heating is slightly reduced, and the radiative cooling is increased. And then here we're seeing basically the results for the entire bulk layer between 0.5 meter and 8 meter here. But it's really interesting to me how what sticks out is here actually that the radiative flux divergence is not just important during the night, and oftentimes the question, how important is radiative cooling near the night? But it actually turns out that the radiative heating during the daytime might actually play an important role of transporting heat into the near surface layer. I can then summarize this also in just into profiles. So for day and night under clear sky conditions, and what you're seeing here during daytime, we have very strong super adiabatic layers. You're seeing very strong heating near the surface, and then during the nighttime, we're seeing the same results as we're seeing in the modeling, with actually heating near the surface and the cooling above. And so now you might recall that elevated temperature minimum and why I brought that up. So there's strong heating near the ground, and we're seeing this increase in temperature near the surface. So that's why this might be of interest. Okay, and so I can now, of course, compare these radiative heating rates and how they compare with the temperature tendency that we measure with, in this case, it was thermocouples and then ventilated TROH probes as well. And so what's sticking out here first is that the radiative heating here during the day and the night has enormous rates, right? And they do not compare at all with the observed temperature tendency at all, but there's a strong contribution. Seems to have a strong effect. At the layers above, we're seeing daytime radiative heating, nighttime radiative cooling, and it's actually on the same magnitude as the temperature tendency, but it doesn't really fit our to explain the strong cooling in the evening and the very strong heating that is occurring in the morning. So, but these are, and then here I'm giving also the uncertainties of the measurements at the Arizona meteor crater. So now, this is under clear sky conditions. And next I'd like to, these were for me very interesting measurements, kind of probing how important is that, under what times during a clear sky day is radiative cooling and heating important. But ultimately I was also interested in seeing how this radiative transfer affects fog formation, right? And that's why the cold fog amongst complex terrain study, I had this tower there and I wanted to see how it relates to fog. So oftentimes what is the problem when we have tower-based observations? So first of all, it requires very careful calibrations of pyrgeometers, and the measurements are really limited to the height of the tower. During fog conditions, we often want to see what's happening on the top of the fog, right below the fog, and oftentimes the towers are just not high enough to probe into the fog. So we need a new approach for observations. And in the next step, I want to kind of introduce you some ideas that I developed not alone. Ed Cregan was a colleague I discussed it with a lot, and kind of started developing an idea of how to observe radiative cooling and heating from a balloon-borne platform. So there's newly available, very small thermopile pure geometers that are available from Apogee. And Apogee also builds little data loggers that can log just one of these instruments. And they are very lightweight, and they basically invited themselves to be combined with a gimbal that is available for action cameras. So you might see videos, of skiers going down steep couloirs, and they typically have a gimbal stabilized GoPro camera on the helmet or so on. And so if you, the idea was to combine these radiometers that need to always be orientated upwards on a very mobile platform to to keep them stabilized. And that's what we basically did. And what you see here, so you see this gimbal structure, and you see the logger, and then the sensor that is mounted on top. And we deployed one on the top of the balloon, and one here on the bottom of the balloon. This is my colleague Eric Pardiak just getting the radiosonde, the TRH and wind probe ready here during the CFAC campaign. And so the nice thing is the weight of the system is well below 400 grams. Currently it's down. I removed the cable, and Apogee helped me to feed the cable directly into the logger unit. So it's much lighter now. It's only about 320 grams at the moment. All right, but using less sophisticated sensors might also lead to some problems. So what I did is a comparison, of course, of these smaller sensors against the Kip and Sonnen standard here, and you see a couple of days here on the roof in Salt Lake City, comparing the Apogee SL510 to the Kip and Sonnen CGR4, which was ventilated and heated and so on, and this was just sitting out. And we're seeing a fair amount of so-called solar leakage. So there's shortwave wavelengths that are leaking into your long-wave sensor. That's a common problem of these sensors, and aptly with the peer struggled on these, and you need to. That's typical interference filters that need to be applied on the silicon domes, and so that's a known problem. But if you correct actually here for this mean nighttime offset, we're seeing the solar leakages that during the nighttime at least you actually get a very steady signal. As we are really interested in not the absolute accuracy but relative accuracy, as we are interested in the change of the long wave flux with height, we concluded that we can use these sensors. And so next I want to show you an example of the example from the cold fog amongst complex terrain experiment. This was during IOP9, where we actually had a nice ice fog event, or very cold conditions. What you see here was Bill CL61. Here in the background, this is the time height cross section of the backscatter. Here the time, and these zigzag curves here in blue is basically showing you where the tether sound was during the time. And I'm also plotting here the depolarization ratio from the CL61, so you kind of can see when there's changes in the microphysics, or at least the depolarization ratio suggests that. So I want to focus and pull out a couple of profiles here. So this was at 4 a.m. Here on the leftmost graph, I show the temperature profile. Then I show relative humidity over water and with respect to ice. Here in the next plot, I show a liquid water content that is integrated basically droplets from an OPC, an optical particle counter. So this is a proxy for the fog water. And then I can show, I'm showing the net flux. So that's the some of the in and outgoing long-wave radiation measured by the two pyrgeometers. And then here I'm plotting the radiative cooling rate. So here, what we're seeing here is that nice, during these clear conditions, we're seeing what we kind of expect. We're seeing nice cooling here away from the surface. We're seeing a change in sign near the surface and radiative heating. Now, when we introduce fog, we're seeing that this changes, and as expected, we're seeing this nice increase in radiative cooling right at the top of the fog. And so we're very excited about seeing that the sensor system works, and we're seeing we're solving actually this stronger cooling at the fog top layer. We're seeing also that this might actually have an effect in the changes here in the fine structure of the temperature profile. So here I'm showing two consecutive soundings where there's an increase in the fog, and if you kind of look to the left, you're seeing how the temperature evolves. You're seeing how quickly the radiation, the radiative flux it adjusts to that. And now we can kind of do a back of the envelope calculation and saying, how does the radiative cooling contribution here compare with the observed temperature tendency? And so here within 12 minutes, that's the time between the two soundings, we're seeing here a change in the temperature profile that amounts to about 120 Kelvin per day. And if we are looking at our observations, we're seeing that the same amount of cooling is actually exerted simply by the radiative flux divergence that we actually directly observe with our sensors. So it really concludes that under these fog conditions, it's the radiative cooling that can fully control the evolution of the temperature in the near surface layers. Next, I want to show you first tests of the system flown on Sable Island. It's another fog experiment that was actually just a few months after CFACT. I was deployed on a small island in the Atlantic Ocean. It's about an hour flight off Nova Scotia, a small sandbar where we studied marine fog. That was the fog and turbulence interaction, the marine atmosphere project funded by ONR. And here you see a deployment of this tethered balloon here, and as well here as the balloon pops out of the fog. We want to show you some example from IOP5. This is again a time height cross section of the ceilometer showing the backscatter, and you nicely see this fog layer here. And I was actually back in Halifax at that time, and we had the OPC data on the internet via Starlink, and I actually was sitting there and I saw these soundings here, and I saw the OPC signal, decreasing, but not quite popping out of the fog. And we had permission to fly to 100 meters, and so I sent a text message to Eric, please fly just a little bit higher. And so sure thing, he got my message, and he flew a little bit higher, and also the fog layer just at that time contracted a little bit. And so we actually resolved a couple of profiles here as the balloon popped out of the fog layer. And so I'm showing a couple of profiles here. You nicely see here this is a picture actually during the time of the balloon, how it looked near the surface. And you're seeing this layer here, fully saturated fog atmospheric layer. The fog was really confined here to the lowest 80 meters. Again, this is an OPC proxy here, not shown in liquid water content, but in the PM data. And then again, you're seeing the profiles, the observed radiative profiles, and the radiative heating rate that is resulting from this. Now, during this time, the fog layer was actually evolving very quickly. And you can kind of see that here. And I didn't bring the animation, but I have an animation of webcam images from every webcam snapshot every minute. And you see how dynamic actually the fog layer is. So there's a strong variation in the density, temporal evolution of the density and consistency of the fog as it advects by. So it's an advective situation. And so I had to decide on whether to smooth or not smooth my radiative profile. And I just want to show you the effects here that actually the sensor reacts very quickly to, so this is the unsmoothed radiative fluxes. And you see that small variations in the amount of fog water the radiative sensor picks up on that very rapidly and shows the changes in the radiative heating and cooling. So this leads me to, let's see, I have one more. Yeah, here I'm showing the observed and radiative contributions to the cooling. And you're seeing that the observations of the temperature did not respond as fast as actually the radiative signal is responding. So the radiation seems to be driving the temperature, not the temperature, the radiation in this case. So to summarize kind of these two observational approaches, there's, quickly look at the time, there's advantages of doing balloon observations versus tower observations. The balloon observations get us into layers further away from the surface. So in fog applications, that might be more interesting, but it's also a lot more manpower intensive to fly a tethered balloon rather than instrument a tower. However, you don't have to do relative calibrations of the sensors. You can go with your balloon somewhere and take measurements. You don't have to have a week-long relative calibration of your sensor prior to this. So there's pros and cons of both observational approaches. How am I doing for time? We started, I have until 1:15, is that? Okay. All right. Quickly, I have a few more slides on looking at radiative cooling in complex terrain. That was one of the third motivation of why I'm interested in radiative cooling and heating. And so if you look at these topographic basins, you have typically the radiative energy exchange at nighttime is you have outgoing radiation, and some of that will heat the sidewalls. On the other hand, you have counter radiation from the sidewalls if you're looking at the radiative flux near the surface. So the question is whether this radiation from the sidewalls might limit the radiative cooling within topography. And so in order to answer this, I collaborated with Dr. Bernhard Meyer from DLR. He has developed a 3D radiative transfer code called MYSTIC, or the Monte Carlo code for the physically correct tracing of photons in cloudy atmospheres. And basically in this code, physical processes like scattering direction, absorption, reflection are all determined randomly using probability distributions, and you're tracing millions of photons in its path to then ultimately calculate fluxes, and then use these fluxes to calculate heating rates. And what I did here in this work, that I looked at different shapes of topographic depressions, valleys, and basins, and also different shapes, a sinusoidal or a Wittig-Agnesi function. I used different width scales of basins to kind of test why, wide valley or a narrow valley might react differently. And I looked at different boundary conditions, atmospheric boundary conditions here. And here's just an example of a cross-section through here. And I picked a sinusoidal valley, and I picked here the evening, when we have, here's the temperature profile, you start seeing strong cooling, stable conditions here near the surface, and the radiative transfer model nicely resolves the cooling that's exerted by that, but you also see that you have less cooling closer to the basin sidewalls. And here, these are basically heating rate profiles, radiative heating rate profiles in the mean of the basin cross-section at the center, and then as a reference here in blue is what the radiative heating rate would be over flat terrain, over reference flat terrain. And so when you do this, you can kind of draw conclusions over what these sidewall effects in different sizes of topography have on the radiative heating and cooling. And so this is now for the center of the topography. And what you nicely see here, so in the center of the topography here, the reference flat terrain is now in black, the basins in blue, and the valley in red. And so you nicely see that after the valley or the basin becomes wide enough, is that the radiative cooling rate actually approaches the flat terrain solution. However, if you want to integrate over a valley and you want to see how the cooling affects the whole cross-section of the valley, you can kind of look at the layer mean. And again, here the flat terrain is in black, and you see that even radiative cooling, effects on sidewall effects can still be observed in basins in the order of a 5 kilometer scale. All right, and so this was my last example, and I'm coming now to the conclusions. So there's some general conclusions. So long-wave radiative flux divergence is often on the same order of magnitude of the observed temperature changes, and it seems to play actually a quite important role in determining the temperature and the temperature gradient near the surface. There must be, of course, an interplay with the other terms in the temperature tendency equation. We can observe radiative flux divergence both during day and nighttime, so it's not just a nighttime phenomena, but these observations only show that this radiative heating plays a role of affecting the near surface temperature during the daytime, and it's dominated typically by the outgoing flux. Radiative flux divergence can be directly measured either on meteorological towers or with these newer developed combination leading to these balloon-borne sensors, and these different observational approaches have disadvantages and advantages as discussed. And what is important is that radiative flux divergence, the model calculations really are highly sensitive to the exact structure of your temperature profile. So changing, so the fine structure in your temperature profile will have a huge effect in your magnitude of radiative heating and cooling. And with respect to fog experiments, is that the balloon-borne flux divergence observations are successful into highlighting the strong interactions between fog and radiative cooling. And under the ephemeral fog conditions that we've seen in the Heber Valley, radiative cooling is definitely a dominating term in the temperature tendency equation and can account for the observed cooling during variations in the fog occurrence. Looking at terrain effects is that terrain features can limit the radiative cooling, and these calculations with the MYSTIC 3D radiative transfer curves really showed how that could quantify how radiative heating and cooling varies within topography. And in topographic depressions, the nighttime cooling is reduced by the back radiation from the sidewalls. But if you're at a distance of about 2 to 5 kilometers, that's when the radiative cooling profile in the center of a depression will match the radiative cooling and heating that you would see over flat reference terrain. One more slide here for future ideas, future work. There's always a lot more to do, and we have I showed that we have tower measurements during the CFAC campaign, where I showed you the profiles of radiated flux divergence from the balloon. So next step is really to also make sure to harness those observations, those continuous observations that are made on this tower. There's also additional data that was collected on the balloon platform on the tower that helps inform about the variations of the fog, like droplet size distribution. The dipole ratio might tell us something about the microphysics to further observe these radiative interactions. And then, of course, the tower observations also included observations of sensible heat and latent heat fluxes. So ultimately, the next step is to calculate sensible heating and how that relates and interacts with the radiative heating. So that's big on my bucket list to investigate further. And currently, I'm planning to send the balloons borne system to fly in the Swiss Mittelland on Ulrike Lohmann's Cloud Lab balloon. And here's also a conceptual idea of mounting this on the system on drones. And of course, there's still the elevated temperature minimum that might be that I would like to link to some of these processes, may be the radiative heating contribution to the surface or not. Okay, so with that, I want to just acknowledge funding sources, and thanks to my mentors and mentees for contributing, lots of colleagues that helped with these observations. And definitely want to stress the NCAR and EOL support. Thank you for inviting me here and helping to make these measurements successful. And really everyone involved in the field campaigns. So with that, I'm going to thank you very much, and I'm happy to discuss.
Thanks, Dr. Hoch, for that very interesting seminar. If you're online, reminder, drop your questions in Slido at the bottom of the screen. Do we have any in-room questions?
Nice, you showed that LiDAR observations. Just have a question on the LiDAR measurements. Was it attenuation corrected, what you showed, the beta, when you showed that backscatter measurements? Is it corrected for absorption or attenuation?
So the ceilometer observations,
okay.
Are they corrected for?
Absorption. In the cloud, because of fog you have there, right? Uh-huh.
It's basically a simple backscatter,
okay.
backscatter effect coming out of the ceilometer. So there's
okay.
no, I've not applied any specific corrections of the backscatter, but I think the backscatter profile shows you whether there's cloud particles or not. So we have a higher backscatter or not based on the backscatter, but you might miss the exact intent of the question.
Okay. About the dipole measurements, is it the same instrument?
It's
basically?
the same instrument. It's the new CL61 bisolar ceilometer, and I'm actually not an expert on those observations. Maybe Bill can chime in there. He provided that instrument, but I just used the data as out of the box.
Okay. Thank you.
I haven't done any specific analysis or corrections for the sensor.
Okay.
And of course, and you've seen here too, there's some white spots in there, and so the ceilometers tend to have issues very close to the sensor. The fog was very thin, it was a thin layer, so the first
Thank you.
Thanks. Any other questions in the room?
Hey, Sebastian, thanks. That was great. So I understand that the models have a really hard time with making fog and breaking up fog. Can you just speak to us what you think is missing in the models and how that relates to what you were finding with your measurements?
So I'm not a modeler, I'm more the observationalist. So everything I say here is a bit speculative. And so we're really still in the phase of analyzing the data, compiling things. And my model partner actually, or on the team, was recently here and gave a presentation, Sao Chapu. I think I think there's a recording of a talk here, and she's probably more the expert in answering this question. I think with respect to my interest in the radiative transfer, I think it's difficult for the model to, as the radiative transfer is so dependent on the fine structure of your temperature. The current models that are predicting fog near the surface, if you look at the data points here, the resolution near the surface, it's not the resolution that you would need to properly observe the or resolve the radiative cooling and heating near the ground, or even that elevated temperature minimum you might see during clear skies. The first model grid point, as you know, is probably a few meters above the surface and well above that layer where that is exerted. I do also think that there's improvement in the turbulence, improvement needed in the parameterization of turbulence, and these are not results from the project here, but there's new parameterizations of turbulence that have shown in the past and past applications, for instance in the Swiss Midland, to be helping in the proper prediction and the successful prediction of fog occurrences, but we have not tested them in the framework of the CFACT campaign.
So does the measuring radiative transfer on towers, does that also suffer from just the shadowing of the structure itself? Is that something you have to account for?
Yes. So it's not necessarily the direct shading because we're in the infrared, but there's definitely emissions. So the tower has a certain temperature, and the tower is in the 360 field of view of your instrument. So there's a flux contribution of your sensor that is due to the tower. That is something that can be corrected, and there's a paper, the 2007 paper, shows an example of how that can be done. There's again some assumptions. You can either have a temperature, if you measure the temperature of the tower structure itself, and you know the emissivity of the tower, then you can calculate the flux contribution from your tower section and try to correct for that. So, but yeah, that's absolutely the case, that you introduce problems, and of course that is something a pro. If you're measuring this on a balloon, that you have a fine line of your balloon, and that is not going to obstruct the field of view, and so that's definitely an advantage of doing these measurements from a balloon-borne platform. You still will have the problem with the representativeness with the field of view. So as you bring the balloon up and down, there's different fields of view of the instrument.
Anyone else in the room? All right. then I guess it's my turn. So you mentioned possibly using UAVs. Do you have ideas of how much you could fit on the payload or specific sampling strategies you might go after with that?
I personally, I have never used a UAV. This was a UAV. We just tried it. There's some issues with, the gimbal itself has magnets in it that those magnets need to be properly shielded in order while you do the calibration. For the drones, and even don't know the proper lingo to use here, but to calibrate the compass and of the inertial compass of the drone, so that can mess that up, and so, but the instrument is lightweight enough to be flown on drones, and of course there's drones of different sizes, but the mid-size drones, like drones that are used by, I think there's a company in Switzerland that now flies drones to replace weather balloon soundings, and these drones would be capable of carrying that payload of another 360 grams. In this case, this is a one down-facing sensor. Ideally, you have an up-facing and down-facing sensor at the same time. You would want to have the sensor to be above your blades, right, looking up and down. But I think it definitely the weight should not be a limiting factor of trying to use those on a drone. So if anybody has a drone and wants to test it, let me know. I'd love to provide the sensor package and collaborate.
Great, thanks. Well, if there's no other questions in the room, it is 4:30, so let's thank Dr. Hoch one more time for that interesting seminar.
Thank you so much.